Hello students, Dr. Shragi here, and we're continuing now in Module 4 of ATS 564 and Energy 301, and we're going to be starting to talk now about ways of describing the variability of a data set. Just to review what we've done so far, remember so far we have reviewed the basic terminology of our descriptive statistics. This was like learning about what was a statistic versus a parameter, population versus samples, and so on. In particular, we really have dwelled on this business about the difference between a statistic and a parameter, how parameters are a property of the random variable itself, the phenomenon that you're trying to understand. Statistics come to us based on the sample that we've taken. We calculate statistics from our numbers that we have seen as part of our experiments or whatever. And then we have learned about different ways that we can understand and estimate the mean. In particular, we learned about like averages and medians and modes and so on. But now it's time to start to actually try to learn about ways to describe the variability of a random variable. How different one instance of one numerical event can be from another numerical event, or one observation can be from another observation. And once again, we're going to see the same pattern here, where there's going to be parameters that can describe the variability of the population, whether real or conceptual, and then there will be statistics that we calculate based on the sample that we take to describe the variability within the sample. One key parameter for describing the variability of a random variable is known as the variance. Now the variance is denoted with the symbol sigma squared. And the squared is going to help you realize that one of the important things to know about variance is that the units of variance are always the square of whatever the units are of your random variable. For example, if you have a random variable that is like, let's say, energy, like maybe you're talking about the amount of energy produced in each day on a wind turbine or something like that, if your unit of energy is then joules in your random variable, then the units of your variance are going to be joules squared. Okay, and sometimes these units don't seem to make a lot of sense. I mean, if you're talking about measuring your random variable as the height of Creighton students, and measured in, let's just say, meters, then the variance of them is in meters squared. It can be a little hard to think about that, but as long as you remember that that's the way the units are going to work for variance, you'll be fine. Variance is a nice parameter. Variance is a parameter that can be derived. A stats major learns how to derive the variance of a random variable. It's a complicated process, but in the end, the parameter works the way you expect it to work. For example, it's going to be bigger when the data set has more variation in it. It's going to be a smaller number when the data set has less variation in it. It's going to be 0 when there is no variation at all, like when your random variable is actually a constant. I mean, that's kind of the properties you would want your measure of the variability of a data set to have. But it turns out variance is actually a lot like the mean in the sense that it's the kind of thing we all kind of know what we mean, but it's actually difficult to define. Again, in Mathematical Statistics 561, they actually learn how to derive the so-called moment-generating functions, and then they integrate them over certain domains. And yes, I mean, it can be done, but we just kind of have to have a little intuition here that this idea, variance, describes how spread out the values are. We're not going to get into the business of deriving these things or something like that. It turns out to be remarkably difficult to do that kind of thing, to define what we mean by variance. But it's a real thing. It's a real parameter of a random variable. There is some real spread to the data. From one day to another, the temperature is different, or from 1 hour to another, the amount of power the wind turbine is producing is different. There is a real property of the random variable that is the variance. That's a parameter. We have a statistic that can estimate the variance. It has the rather uncreative name of the sample variance. The sample variance is an estimate of the variance, and it is a fairly straightforward, if slightly messy, equation to compute the sample variance. In this case, here on the left-hand side, you can see sample variance is denoted s squared. So the sample variance of, say, random variable x will be s squared of x, and then you can see here the notation of it. It is the sum of the squares of the anomalies. Oh my, this is a lot of terminology here. See how we take xi, the ith observation of x in our sample minus the average, x bar, and we square it. Then we add them all up over from I equals 1 to I equals n, and then we divide by n minus 1. It's a fairly straightforward procedure. It's just sort of, might not be immediately intuitive as to why it works that way, so let me do a little example that just kind of illustrates it. Here I've just made 8 numbers. I just pounded them out on an Excel spreadsheet there, okay? There's my 8 observations of some property, all right? And I plotted them on the little plot right there, 1 through 8. Okay, now, just to make this a little bit easier to see, I'm going to switch the y-axis a little bit here so that I've kind of expanded the domain. You can see better the differences between the lowest and the highest observation and so on. Well, there is an average to these 8 observations, and I computed it. It happened that x bar for these 8 observations, x1 through x8, was 50.25. Okay, so I have drawn a line on my graph here. I'm going to be illustrating how the sample variance works using this graph and this line. Alright, so graphically we can see that's the average of the 8 little diamonds, the 8 little observations that I've taken so far. Okay, now what I want to do is I'm going to draw a little stick, if you will, from each of the observations to that average, okay? And each of those little black bars or each of those little black sticks is telling us how far away that observation is from the average. This is x of I minus x bar. Some of them are positive and some of them are negative. The right word for those little differences between the actual observation and the average is called an anomaly, by the way. So we have the anomaly. How anomalous is this observation? How far is it from what is typical for the sample that we got? So we have 8 little anomalies here, the distances between each of the observations and the average. Okay? If we just added those observations up, they would just be equal to 0. There's some positive ones, there's some negative ones. If we added them up, they'd be 0. It's a simple little proof to prove that if you wish to. But if you added up the squares of those anomalies, then you get something interesting. You're starting to get to measure the variance. See, when we square them, they're all positive now. The ones that are farther from the average weigh more than the ones that are closer to the average, and you start getting a measure the bigger this sum of the squares of the anomalies starts becoming a measure of variance. Oh, I see. So if I put my equation up there for sample variance, s squared x, alright, well we can kind of start parsing this and seeing how this definition of the sample variance works. I mean, see here, I have the anomaly at observation I, that would be xi minus x bar, okay? I'm actually going to square it so that it's always positive and it gets really big if we're far away from the mean, from the average that is. So the square of the observations at observation I, the square of the anomaly at observation I, okay? Then I just summed them all up from I equals 1 to I equals n, the sum of the squares of the anomalies. And then as it happens, we divide by n minus 1. This is a little bit of mathematical theory of statistics here. We have to divide by what is known as the degrees of freedom. It's not terribly important. You can kind of think of it as like the average square anomaly. It's not quite average. It'd be average if we had n in the denominator rather than n minus 1. But you get the basic idea. And this is giving us our sample variance, s squared, for the random variable x. Now the sample variance is a type of estimator of the variance, and it has properties, just like our average had properties as a statistic. It had properties that it brought to its estimation of the mean, and we would like to understand those properties, just like we did for mean, averages, where we started talking about things like how robust or how resistant the estimator is. And in the case of the sample variance s squared, turns out this is actually a remarkably robust statistic. We won't do a bunch of demonstrations of that right now, but it turns out, remember what does robust mean? It means even if the underlying assumptions about how the data were distributed aren't right, it still works. Yeah, this is no problem. Variance is a real property of the data set, whether the data are distributed in a mound-shaped, bell-shaped type distribution, or exponentially distributed, or uniformly distributed, or any other strange distribution out there, bimodal or something like that. And in all cases, it can be shown that sample variance is a reasonably good estimator of the variance of the population. But it can also be shown to be not very resistant to the problem of outliers. Remember, outliers are going to be those observations that are way out there, far from the average. You know, remember our analogy of like when we were trying to figure out the average, the mean income in Omaha. Well, what if your sample just happens to have Warren Buffett? Well, Warren Buffett would have a huge anomaly, right? The difference between Warren Buffett's income and the average income would be so huge, and then you'd be squaring it. Outliers have very large anomalies, which means they have extremely large squares, and they just totally make this equation for sample variance blow up. You end up with a huge value for the sample variance if you happen to have an outlier. So sample variance is a very robust calculation. It's a robust way to estimate the variance of a data set, of a random variable, but it isn't a very resistant one. Okay, we have another parameter that can help us talk about the variability within a data set, and that's known as the standard deviation. And the standard deviation is written with a symbol sigma, and unsurprisingly, sigma is the square root of sigma squared. I mean, you can kind of see what really happened here. In the world of statistics, sigma was actually, the standard deviation was actually derived and used first, and then variance kind of became something after that. Otherwise, this would not be a very useful notation, right? Our variance was sigma squared, our standard deviation is then sigma. And one of the interesting properties, if you will, of the standard deviation is that this parameter has the same units as the random variable itself. So like if your random variable is, say, you know, energy produced by this wind turbine and it has units of joules, then your standard deviation also has units of joules. Or if your observation is rain rate in millimeters per hour, then your standard deviation of that rain rate is also in millimeters per hour. But it's a pretty straightforward thing. And standard deviation works the way you would hope a measure of variation would work, in the sense that it's bigger when there's more variation. If the variation is less, then standard deviation is less. Standard deviation is a positive definite quantity, so it can, if it's zero, it means there's no variation going on. The variable is a constant, and so on. Okay, so standard deviation is another related measure for it's a parameter of a data set that explains that describes its variation. Again, it's a parameter. We don't necessarily know what the value of that is, but there's a statistic that we can compute based on our sample that we can compute, and it has the unfortunate name of just being the sample standard deviation. And the symbol for sample standard deviation is just an S. It is an estimator of the standard deviation based on the sample. And again, the equation probably is not a huge surprise to you here. If our symbol for like the sample standard deviation of random variable x is just going to be Sx, well, it's just going to be the square root of our sample variance, which was S squared of x. In other words, it's just the square root of, and then that whole big equation that we use to compute the sample's variance. Okay, well, I mean, it's messy, but it's just arithmetic. I mean, there's no calculus here, there's no fancy schmancy mathematical operators or anything like that. And much like sample variance, sample standard deviation is a pretty robust statistic. There's a reason why this is one of the statistics right up there with average and stuff like that you've heard of before. Okay, even if you don't really have a good idea in advance of like what the distribution of your data is going to be or anything like that, it turns out sample standard deviation is still a pretty robust estimate of what the true standard deviation of the random variable is. But much like was the case with the sample variance, it is not a very resistant estimator of the true standard deviation of the data. An outlier quickly makes the sample standard deviation much, much larger than, it isn't a very good estimate then of what the true standard deviation of the random variable is if you just happened to get an outlier in your sample. One thing I want to bring up here, remember how back when we talked about averages and mean, I mentioned how people, even textbooks, even journal articles and so on, often confuse the term average and mean or use them interchangeably or something like that, despite the fact that they're not the same thing. It's very common to use the terms interchangeably. We're going to have the same problem when it comes to standard deviation and sample standard deviation, or variance and sample variance. It's remarkably common to make the mistake of thinking that these are the same thing. Even in textbooks, mistakes will happen. I had to be very careful on my notes that I'm using for this lecture to make sure that I don't make that mistake, and I probably still have some slides with mistakes on it. Especially when it comes to the symbols, it's very common for people to use them interchangeably. It's very common even in like scientific journals or in textbooks or whatever, lectures or whatever, for people to use the symbol sigma, which is the variance. Well, sigma is actually standard deviation, sigma squared being the variance, when they really mean S for sample standard deviation, or S squared when they mean sample variance. So kind of watch out for that. Like if you're Googling to find some documentation about how to work with this stuff in Octave, oh my goodness, they're using S's, but I know they mean sigmas, or the other way around. Be alert to the fact that I think even in your textbook, even on web pages documenting Octave and so on, there's going to be misprints and mistakes where people have used the terms interchangeably. How about some other ways to describe variability? I mean, we focused so far entirely on the standard deviation and the variance. Are there other ways to do it? Well, there are some that are based on techniques closer to like what we did with the median. For example, here I made a little data set. I have sketched out here, just messing around with Excel for a little while. I made 100 observations, and here's a histogram of what they look like, showing the distribution of them. For what it's worth, they range from 10 to 30. There was one observation at 10. There was, whatever, I don't know. Let's say this is temperatures or something like that. So like at 10 degrees one time it was observed, all the way up to 30 degrees one time it was observed, but like the mode of the distribution appears to be at about 20 degrees where it was observed 10 times. If I did the math there, it worked out that the average of this data set was 19.51 degrees. For what it's worth actually here, if I actually computed the median of this data set, x tilde, it's 19.5. Which, by the way, is awfully close to that 19.51. Once again, just by pure chance, I've gotten my median and my average to be remarkably close to each other just by accident. What does it actually mean that the median is 19.5? It means that 50% of the observations in this data set are less than 19.5, and 50% of the observations are more than 19.5. Okay, we talked about medians extensively in the last lecture. That's not necessarily all that surprising. But what we can do is we can extend this idea. Instead of breaking up the data set into two pieces, each of which that contains 50% of the observations, what if we divided it up into 4 pieces instead? So like here you can kind of see with these boxes here, I try to divide it up, where I said, okay, 25% of the observations are less than 16.5 degrees, and then another 25% in that black box there are between 16.5 and 19.5, and then another 25% are between 19.5 and 22.5, and then finally another 25% of the data are greater than 22.5 degrees. Okay, so I've broken that up into 4 little boxes. They're not of equal size on the x-axis or equal size on the y-axis, they're of equal size in the sense of like the area, total area under those histograms. The total number of observations, as it happens, there's 25 observations in each of those, okay? The lowest 25 are in the red box, the highest 25 are in that darker red box, and the other 2 groups are in the black and the green box. This idea of breaking the data set up into 4 pieces like this is called quartiles. We've just divided the data set up into 4 quartiles. Quartile, it's got the indication there of being 4. Okay, so I can think of it here as like I've divided this up into 4 groups based on where the 25th percentile of the data set is. In other words, 25% of the observations are less than this. Or the 50th percentile, where half of the observations are less than this and half are more. And then finally the 75th percentile, where 75% of the observations are less than this and 25% are more. We've broken the data set up into these 4 pieces here. Now, I'm telling you about this because there turns out to be kind of a sneaky little way to get a sense of the variation inside of the data set based on this idea of breaking the data up into quartiles. Because the difference between the value of the 75th percentile and the 25th percentile is kind of a measure of the variability. It kind of tells you how wide the distribution is. The distance between that 25 and that 75th percentile is called the Interquartile Range, or the IQR. it's kind of a low math way of coming up with an estimate of the variation in the data set. In this case, the 75th percentile was 22.5, the 25th percentile of the data set was 16.5, 22.5 minus 16.5 is 6 degrees. So in this case, our interquartile range is 6 degrees. If we had another data set and its interquartile range was bigger, maybe 8 degrees or something like that, that data set would have more variation in it than a data set with a smaller interquartile range. Kind of a nifty trick. Now, strictly speaking, interquartile range is actually, it's a measure of the variability in the data set, but it is not an estimator of the variance, as in that parameter, the variance of a data set. It is not an estimator of the standard deviation or anything like that. It's a measure of variability, but it is not actually an estimator of one of those parameters that we know so far. The big advantage of the interquartile range as a measure of variability is that it is extremely resistant to the problem of outliers. If you have some outliers out there, all that does is just put one out there in the tails, okay? It doesn't, if you had on that graph there that we had with the temperatures from 10 to 30, if one of our temperatures was -10, okay? All it does is just put one more observation out in the tail. It doesn't move with the interquartile ranges much of any at all. So the interquartile range themselves, the value of the 25th percentile, the value of the 50th percentile, and so on, is actually very resistant to change. You know what's something that they measure a lot using these kinds of like interquartile ranges and so on? The growth of children. When you take your child to the pediatrician some fine day, they're going to weigh your child and they're going to put him on, measure his height and so on, and they're going to tell you that your child is at the 33rd percentile. Okay? That means 33% of the kids are shorter than your kid, and 67% are taller than your kid. Or your kid's weight is at the 53rd percentile. That means 53% of the kids are weigh less than your kid, and 47% of the kids weigh more than. And you know what? It doesn't make any difference to those numbers if there's like one really heavy kid. Yeah, maybe there's that one kid who's just really, really big, but you know what? He's at the 99.9th percentile. That doesn't move the percentiles. My kid isn't lighter because that kid's in the sample. Okay? That kid is just, he's out in the tail of the distribution. He doesn't move the percentiles. It's this idea of interquartile ranges and percentiles and so on are very resistant to the problems of outliers. While we're on this idea of percentiles and quartiles and so on, I just wanted to draw your attention to a terminology issue here. We can divide up our data set into 4 quartiles, where each of the quartiles contain 25% of the observations. We can generalize that and divide it up into as many pieces as we want, as long as they're equal sizes. We could divide it up into 6 pieces, or 8 pieces, or 10 pieces. And the right word for that, those pieces that we divide up, is that they are quantiles. Okay, notice quan like quantity versus quar as in quartile. When we divide them up into a number of subsets like this, each equal in size, the right word is we divided the data set up into quantiles. Okay, I just know that the textbook drops that word quantile more often than you would think. And speaking of the textbook, there are actually other ways of describing the variance of a data set, or the variability of a data set, that are described in the textbook. The lectures are getting long enough. We don't need to go into all the details. If we need to compute some of those other measures of variance, well, they're in the book. We'll direct you to the pages. But more than just talking about the variance, I also want to talk about the shape of the distribution. We have statistics. That's a real parameter, right? A real parameter of your random variable is the shape of the distribution of like its histogram or whatever. Is it mound-shaped? Is it exponential? Is it bimodal? Something like that. Even if it is mound-shaped, which we'll focus on ones that are mound-shaped, how is it centered? Is it skewed off to one side? How tall is the middle versus how long are the tails, and so on? The shape and character are the terms that we use in statistics. The shape and character of the distribution matters, and the sample should be able to give us some information about that. Now, there are lots and lots of statistics that you can compute based on a sample, where you can be making inferences about what the shape and character of a distribution are. we're just going to look at one example of such a statistic right now. A statistic that describes how symmetric the data set are. If there's sort of a hump to the distribution, are the two sides of the hump equal in size? The symmetry of the distribution is described by a statistic with the interesting name of skewness. Skewness is given by the Greek letter gamma, lowercase gamma. And we have a little diagram here that I confess I got off of Wikipedia of all places, just because it was well illustrated here, to describe what positive skew and negative skew look like. See how there's sort of a dashed curve on both of those? Like there's sort of like a little dashed bell curve there. The negative skew has more observations on the left side of the hump in the distribution than you would normally expect, and the positive skew has more observations on the right side than you would tend to expect. You can kind of see that on that red curve there. That's what we're talking about, skewness. Most random variables aren't perfectly distributed as a nice little bell curve. They have some skewness to their distribution. There's a nifty statistic, the skewness, given by lowercase gamma, and it's got an equation here that looks a heck of a lot like samples variance. But I do want to call your attention to the fact that these are cubes, not squares, that are in here. And I mean, it's just cranking out the math to get this to work. It's clumsy, but it can be done, and there's octave functions and so on that'll help us and so on. But okay, we've got the skewness. So for example, I just sort of threw together a fake little data set here, and you can see that this should have you can see that there's a skewness to the data, right? There's sort of a big fat tail to the distribution off to the right, whereas it just tails off to the left. I should get a positive skewness here, and I do. I got a skewness of 0.12. Okay, so the skewness is one way that we could describe the shape and character of a data set. There's a whole mess of these kinds of statistics out there. Some of them are easier to compute and some of them are harder. For example, a much easier statistic to compute and describe this, the symmetry of the data set is called the Yule-Kendall index, which is given by gamma yk. That's awkward, gamma yk. And Yule-Kendall index is just based on the interquartile ranges and so on. This notation of Q.75, that's the 75th percentile of the data, and then Q.5, that is the 50th percentile, and then Q.25, that's the 25th percentile, and you just crank it through here and you get this nifty little gamma yk index that describes basically what it's trying to do here is just trying to show you the difference. What is the difference in the size of the third quartile versus the second quartile, as a way of explaining is the data distributed in a way that's like very symmetric or very asymmetric. Pretty straightforward. Like I said, there's actually a whole mess of these kinds of statistics out there that can be used to describe the shape and character of a data set. What kind of distribution is it drawn from? And a lot of them have weird names like kurtosis and so on. Again, we're not going to actually take time in the lectures to show you equations for things like that. If we come across problems where we need to know about kurtosis, we'll find the section in the book that's about kurtosis. Okay, skewness and kurtosis are two very common statistics that are used to describe like how bell-shaped a data set is. Okay, but yeah, we'll find it in the book if we need it. Okay, before we end this lecture, I want to ask you a couple questions and see if you've gotten what you needed out of this. Question 6. A negative sample standard deviation. You computed the sample standard deviation, you got a negative number from your data sample, would mean A, the data distribution is skewed to the left, B, the data distribution is skewed to the right, C, the interquartile range is also negative, or D, there is some error because sample standard deviation is a positive definite quantity. A curious question. Go ahead and look at the 4 choices below, follow one of them, and get some feedback on your answer before you move on to question 7.